Hello students, welcome back. Let us resume our discussion in section 1. We went through the divisibility concept and some theorems associated with divisibility. I don't know whether the term theorem is really appropriate for these. These are a bit too trivial, but in any case, that's the term our textbook author is using. The proofs are left as homeworks for you. Please remember all those results. And then let's do some further exercises. Prove the given statement, and okay, how about this one? We have a necessary and sufficient condition problem here, which means we have two implications. If 2 divides n, then 2 divides n squared, that's one direction, and also vice versa, backward direction. So the proof consists of 2 parts, the forward direction and the backward direction. Make sense? All right, let's consider the forward direction. Oh, by the way, what do you mean by this? This means n is even if and only if n squared is even. You see, 2 divides a certain number. That means that number is an even number. Okay, how do I prove this? So 2 divides n. What do you mean by 2 divides n? N is 2 times some integer. Then n squared is 2 times some integer. And that's basically what we want, right? If n is an even number, 2 times some integer, then n squared is also even, 2 times something, whatever. How do you prove it? Well, n is known as 2q, so if I just square it, then this is 4q squared, and this can be rewritten as 2 times something. And that's a proof. N squared is 2 times some integer, so n squared is even. N squared is divisible by 2. That's the whole proof, actually. And that's what I wrote here, except that I used k instead of q. That's it. That was easy. How about the next one here? The other direction. So 2 divides n squared. So n squared can be written as 2 times something, 2 times some other character, let's say j. Then n should be 2 times some integer. How do I do that? Looks pretty challenging, and I cannot take the square root. Square root of 2 is not even a rational number, let alone an integer, so we can't do that. Any idea? Somehow you work it out as n equal to some 2 times integer. If you have some idea, then stop the playback and try. If you don't, then I'll give you a hint. Try a proof by contradiction. Start by negating the conclusion. Actually, it's the other direction, so this is conclusion. Negating the conclusion and try to drive some contradiction or whatever. So let's suppose that 2 does not divide n. Oh, here, here's a full statement here. And do some work so that 2 does not divide n squared either. So that's what you should try. Basically, proving the contrapositive. So if the conclusion is false, then something is wrong, and that something is going to be, in this case, the assumption. So condition is wrong. How do I rewrite this in terms of equality? 2 does not divide n. If you get that, then that's gonna be more than halfway through, actually. So 2 does not divide n. What do you mean by that? That means n is equal to an odd number. Does it make sense? If it is an even number, some 2 times some integer form, then it's divisible by 2. If it's an odd number, 2j plus 1 form, even plus 1, then it's not divisible. So every whole number is either even or odd. Actually, every integer is even or odd. So it works out this way, and from this point on, we can do some algebraic manipulation. What's n squared? 2j plus 1 squared. Excuse me, I forgot the equality sign. And that you can break it off using whatever method you want. Here's a complete square formula. Or you can follow those out if you want to. In any case, that's the final result, so that we have 2j squared. Oh, excuse me, I'm forgetting 2. Plus 2j plus 1. And what do you have? N squared is also an odd number. So the desired conclusion follows. Make sense? We wanted to prove this, the counterpositive, and the dot 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 part, yes. We successfully filled in that dot 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 part, which I just highlighted in red. So even, so assume the other, odd, and then work out algebraically. Here's the proof, and you can see I'm using exactly the same argument, except that I'm using k instead of j. Okay, that was a good exercise. How about the next exercise? Well, that's left to you actually. I hope everybody will see that this is actually a counterpositive of the previous. Negate this, and we get that. And negate this, and we get that. And as for the arrow, they're both double arrows. So direction does not matter. We have counterpositive one way or the other. So A and B are equivalent. If you proved A, then B follows. Okay, all right, how about C? Square root of 2 is not a rational number. Well, this is a number theory, so most of the time we do integers, but this is one of those rare occasions we are dealing with rational and irrational numbers. But eventually everything will fall down to integers, because what you mean by a certain number is rational. It can be written as an integer over integer after all, and that's the starting point. Assume square root of 2 is a rational number and express it as an integer over integer, and the denominator, of course, is non-zero. Moreover, let's assume this is simplified as possible, so the numerator and denominator are not, they do not have any common factor anymore, so they are relatively prime. We will define this relative prime, this business, and the lowest term in a lot more rigorous form sometime next week. For now, let's just accept this. And then we're going to derive a contradiction through the following 4-step process. I said, but maybe it's 5-step process, we'll see. 4-step and then just conclusion maybe. So how do I get that? Well, express it as a fraction and then remove the denominator, m squared equal to 2n squared. You see, this is number theory, so we don't really want fractions. So remove it. Now we have all integers, so we can use some number theory. And we are doing divisibility, so we're going to use divisibility at some point. So what conclusion can you draw? M squared is divisible by 2. That's what we did. M squared is an even number. That's what I got. Now, if you remember what we just did, m squared is an even number. That means m is an even number as well. Haven't you done it before? Yes, so m must be even too. Here I reproduced the proof, but I don't think that's necessary because we already did it. So m squared is even, so now m is even. Okay, m is even, which means here I'm going to plug in m is 2 times some integer. M is 2a. And I'm going to plug in 2a right here. So m squared is 4a squared. All right? And 4a squared will go right here. Excuse me, m is 2a. 2a goes here. M squared is 4a squared. So 4a squared go right over here. So 4a squared is 2n squared. You see this one here? I just highlighted in purple. Purple, right here. M squared is 4a squared. And 2n squared is 4a squared after simplification. N squared is 2a squared. So n squared is even. N squared is even. Coming back to this again. Consequently, now n is even. So n is even. N is even. And m is even. Both the numerator and denominators are even. So they can be simplified further, and that contradicts our assumption that this is the lowest terms. So we went through the proof that square root of 2 is irrational. And what did we use? We used this multiple times. Once for denominator and once for numerator. Consequently, both are even numbers. Both are divisible by 2. Therefore, what we started as the lowest term is not longer lowest term, so we have a contradiction. Now, if you have square root of 3 is irrational or square root of 5 irrational, square root of any prime is irrational, you can follow pretty much the same fashion, except that instead of considering the even versus odd, you'll have to consider the remainder 1, remainder 2, remainder 3, remainder 4. You have to consider those 4 cases when you're doing square root of 5. And if you're doing square root of 13, you have to consider remainder 1, remainder 2, remainder 3, or 2, remainder 12. Those 12 cases, and so on. Similar idea, but pretty soon things will get out of control, complicated. We're going to have to do a little bit better, and indeed we will do a little bit better as we did over here, but that's something that have to wait. Eventually, we can prove that every square root of an integer is either integer or irrational right away. So if you have a square number to begin with, then it's an integer, otherwise all irrational, but that'll have to wait. Okay, so much for that, and we have the division algorithm left. We'll talk about it in the next video, or maybe next 2 videos, we'll see.